My name is Andrew McCaskill. I'm with Gamry Instruments. Joining me are Radek Novak with Kalibric and Yuri Vana from Pinflow. Gamry and Kalibric have partnered together to provide high-power EIS instrumentation, supporting fuel cell, electrolyzer, and battery research and systems. Pinflow develops energy storage systems and research systems, primarily for redox flow batteries. And today Pinflow is going to give a talk about and demonstrate some of the benefits of employing EIS techniques in their stacked mode experiments. So I'll go ahead and shortly turn over everything here to Yuri. And then just after Yuri gives the talk and demonstration, Radek wanted to say a few words as well, and then we'll open up the floor for questions. So during the talk, if you do have any questions, please submit them through the chat, and we can condense some of them and answer them at the end of the talk. And if you wish to ask the question directly at the end of the talk, you can use the raise your hand feature, and we'll call on as many people as we can. And with that, I guess I'll turn it over here to Yuri and let him get started.
Thank you very much. Hello, everybody. Welcome in Pinflow Energy Storage. I'm Yuri Vrana. Together with Jiří Charvat, we will show you our systems, the redox flow batteries, together with Stack EIS. We are in the heart of Europe, actually, western direction from Prague. Regarding few facts about us, well, in Czech Republic, we have very strong tradition in electrochemistry. We are following our Nobelist, Jaroslav Hejrovský, that had invented polarography. But as I had mentioned, we are physically in Pilsen. Perhaps this name of this city sounds familiar for you, especially for those who like beer, because Pilsner is one kind of beer. We are dealing with redox flow batteries that are technologies that store energy in electrolyte. And when we will calculate the energetic value of Pilsner Urquell beer, it is getting something like 240 watt-hours per liter. So that is actually the energy stored that I plan to release today. But let's talk more seriously. So welcome everybody in Pinflow. We will be talking about redox flow batteries. Our company was founded as academical spin-off from two Czech universities, where we were developing the systems completely from scratch. Redox flow batteries are focused on stationary energy storage. I will later describe the technology in detail. We were starting from very small systems. We went through all the stages of laboratory scale-up process of stationary technologies. So we were starting at lab scale, then we were working with semi-industrial scale. We come from the University of Chemistry and Technology in Prague, but the scale-up process was mainly conducted at New Technologies Research Center under the University of West Bohemia, where we have developed 2 kilowatt redox flow battery stack, and later we have spun off Pinflow, where we have gained the license on the utilization of that academical know-how that we have gained as a researchers. Now we are in a nice manufacturing hall, and we are delivering our products for researchers from laboratory scale through semi-industrial scale up to industrial containerized demonstrator solutions of redox flow batteries. But what is redox flow battery? Well, actually, it is a flow electrochemical technology for energy storage. It is tailored for stationary application. And we are pumping liquid electrolytes into the redox flow battery stack, where electrochemical reactions occur. We are always pumping positive and negative electrolyte, and inside the battery stack, we have inert electrodes, and on their surfaces, the electrochemical reactions occurs. So we have positive half cells, negative half cells that have inert electrodes. So typically it is carbon, and then we have some active species in positive and negative electrolyte that are reacting on the surface. The half cells are separated by ion exchange membrane, and so that is between the half cells and between bipolar plates that are assuring electrical contact between the positive and negative electrode. So the system geometry of the battery stack is actually very close to fuel cells, but the difference is that we are working with liquid reactants. There is many flow battery technologies with different chemistries, but one of the most common is probably vanadium redox flow battery. We will be working today with vanadium redox flow battery, which comprises vanadium-3 and vanadium-2 in negative electrolyte as electrochemically active species, and vanadium-4 and vanadium-5 in the positive electrolyte. The solution is in acidic environment in presence of sulfuric acid. But why to deal with flow batteries? What is the business motivation? Where is the market for this technology? Well, this technology is actually separating the power from the capacity. So it is very modular solution of energy storage where you can truly tailor the parameters of your stationary energy storage. Typically, we are targeting on solutions where we can utilize the high capacity load. The capacity is given by the volume of electrolytes, and flow batteries are targeting on longer duration energy storage. So from the perspective of the market reality, we are somewhere between lithium stationary storages and between fuel cells. Our batteries are designed from let's say 5 hours to 20 hours of operation. The advantage of flow batteries is that the electrochemical reactions occurs in liquid only on the surface of the electrodes, but all the active components are actually in very nice environment from their chemical nature. It means that also the lifetime of the battery is amazing. The electrolytes in vanadium redox flow batteries do not degrade over time. It means that when the battery lifetime is over, typically caused by mechanisms like erosion, like when the river is getting into the earth, so that is the mechanism that is damaging our electrodes over the long time decay. But at the end of the lifetime of the system, you will just pump out the electrolyte, the vanadium electrolyte, and you can practically immediately or without any major treatments use it in new battery. The rest of the system is also pretty well recyclable. We are using some plastics that are easily recyclable, like polypropylene for construction of vessels and tubing infrastructure, and also for our stacks. And then we have some power electronics and some wiring inside the system. So we can tell about the system that it is pretty environmentally conscious. Another advantages are that the maintenance cost and all the operating costs are very low. The system is reliable in general and doesn't need any action. I had mentioned that the system is also pretty safe. The safety is given by the non-flammability of the system. We are working with water-based electrolytes, and there is no fire risk related to the chemistry inside the system. It means that when the system scale is growing, we can place the batteries also in city, or also the fire distance zones are much lower than in case of lithium-based batteries. When we will look on the specific capacity at larger scales, thanks to the minimization of these fire zones, we have very compact energy storage, especially in the scale, let's say from megawatt hour to larger system. The largest installation in the world counts already several hundreds of megawatts. And there is also a lot of demonstrators in field operation over a few years where the power is above, let's say, 10 megawatts. So truly we are targeting on slightly larger scales where we can fully utilize, especially the longer term or the abundance of capacity in our system. In PinFlow, our story where we are hitting the market with redox flow batteries, we are actually utilizing all of our know-how, all of that research experience that we have gained, and we are turning that into products that can be used for research, development, applications, and also verification of flow batteries. And we are strongly preserving that approach where we are utilizing all scales. We are delivering lab-sized systems for development of new chemistries, for benchmarking of membranes and bipolar plate materials, for development of electrodes, but also for quality control. For working at pilot scale, at laboratory conditions, we have our product portfolio of semi-industrial, let's say pallet-sized products, test benches, kilowatt rigs, where the stacks, the redox flow battery stacks, can be verified. And then we have also the product portfolio of demonstrators. Well, everything is starting always with laboratory research. All new electrolytes, all new materials are always verified in the laboratory. That is the best scale where you can work, because when you will solve the issues of your research, you can verify that in small systems. These small systems, let's say the active area of the electrode can be between 4 and 50 square centimeters. For this small scale, you are typically not having issues with electrolyte distribution inside the reactor, and you can very easily accommodate a lot of sensors into the system. You can measure how the state of charge of your electrolyte is changing through the open circuit voltage cells. You can also utilize the typically the electrochemically active species show some color changes, so you can use photometric techniques to observe the changes. You can also check how the conductivity of your electrolyte is changing when there is some kind of pH change or consumption of H plus in the half reaction. So in general, you have access to all possible data that you can imagine. So this is the advantage as I see the laboratory research of flow batteries. But when we then look on the real installation, the issues in stack are starting. You have practically no information about what is going on inside. And the battery, it typically has some battery management system, BMS, which is monitoring if everything is safe for operation, but typically it considers some industrial sensors, but you have truly no idea about the stack. The issue is that the stack assembly is bipolar, so it means that you are using the bipolar plates that are positive from one side, negative from the opposite side, and you do not have potential control on your electrodes. You just need to rely on electrochemistry, which can include the kinetics on the electrode, the reaction kinetics, and then also the mass transfer. It means mainly convection of electrolyte through your electrode zone. But truly you do not see nothing. You can see just the stack voltage, where the information is truly limited by the amount of cells inside the battery stack. So in order to understand what is going on inside redox flow battery stack, you need to bring some kind of advanced interstep between the laboratory scale and real operational redox flow battery. And that is what we are solving with our product portfolio of kilowatt scale test rigs, where we are preserving all the advantages that laboratory scale can offer, so with all the possible sensors, but we are working with real redox flow battery stack. We are measuring open circuit voltages, open circuit potentials. We can have also UV vis detection. We are checking electrolyte volumes inside the tanks. We are precisely monitoring flow rates. We are also observing the pressure drops. We have also flow control on our pumps, so we can hydraulically characterize our stacks. So we truly see a lot of data from the system. But still the question is, what is going inside the stack, inside the individual cells? And this is something where we are as a PinFlow a little bit unique inside the community. We are developing and manufacturing our redox flow battery stacks, our reactors, with electrical contact on each cell, on each bipolar plate. And we are doing this in our laboratory-sized products, but also in our pilot scale products. And through these electrical contact, we can use a lot of techniques how to look inside. The simplest technique is cell voltage monitoring. Inside flow batteries, we are facing to one, let's say, pretty weird phenomenon, especially for those of you who are dealing with fuel cells. As we are pumping pretty highly ionically conductive, electrochemically active species inside that reactor, actually the current, that electron can, let's say, select if will proceed through the reaction and then through like ohmic pathway of the electrode, or if they will bypass the internal cells through electrolyte manifolds. There is pretty large difference of potential between the first half cell and the last half cell. And this difference of electrochemical potentials of those electrodes inside the same electrolyte are causing the driving force for the migration through the ionically conductive manifold. So that is phenomenon that is not present in fuel stacks, but is also very common in another electrochemical or electromembrane processes in general. Inside our redox flow battery stack, we have the opportunity to monitor what is going on inside through that electrical contact. You can measure the cell voltage distribution, but that is typically not enough. And the fun is starting at the point where you can operate with impedance techniques on stack level. And this is something where we are very proud about our collaboration with another Czech company, with Kolibrik, because Kolibrik is manufacturing truly, let's say, on-demand, reliable product, and based on their experience with inside fuel cell research and on their experience with electrolyzers, they were very capable to amend their product portfolio also for the needs of researcher within the field of redox flow batteries. So the thing what we will be presenting today during the live session is that we have mega EIS, which is actually stack electrochemical impedance spectroscopy. We have the possibility to bring alternated current from the unit on our stack, on that current collectors, and we have the possibility to electrically contact each single cell through the sense electrodes that we have available, and we can see what is going on inside each cell. What we truly like on the collaboration with Colibri is that their approach is, let's say, modular. With their modular approach, they can fulfill pretty broad portfolios of needs. For example, they can amend the load parameters of the system. So you can easily play with the maximal currents. And based on your system, you can always select the optimal system from the perspective of accuracy or precision of your measurement. Then there is another way of flexibility of their products, and that is actually that you can build stacks with truly various number of cells. We are typically working with 20 or 40 cells in pin flow. In redox flow batteries, the holy grail of voltage is something like 100 volts. We are typically not going to longer stacks with more cells, because then there are the shunt currents that are starting to be more dominant. But for example, in fuel cell research or in electrolyzers, you can actually go to higher numbers of cells, and then Colibri have their product portfolio to a variable that you can go to hundreds or perhaps up to 1,000 of cell monitors inside their electrochemical impedance spectroscopy units. But what we are going to present today, that will be the real insight inside the stack. And one of the things that can actually happen, why would somebody need to have this unit? That is, as I had mentioned, you can see what is going on inside. And one of the simulation can be seen actually on the picture on the left at the bottom, where in green we are presenting Nyquist plots of individual cells from our stack. And we have made limitation or clogging inside one channel of that assembled stack, and we just wanted point out how the hydraulic distribution of electrolyte from the electrolyte manifold through the cell flow channels will influence the electricity. And as you can see, all the green cells are pretty aligned. There is some minor distribution of ohmic resistance. Also, the reaction resistance shows some distribution. And here you can see that transport related semicircle, but the distribution of the electrolyte is pretty uniform. That is something what you are not able to see by different techniques. You do not have tools how to measure flow rate inside individual cells. But as you can see in that redly highlighted channel, where we have limited the flow rate, we have manufactured thinner manifold, there is pretty significant increase of the overall resistance, which can lead at the end of the day to uneven distribution of cell potentials inside the system. And actually, this might lead to unwanted reactions. As I had mentioned, we are working with aqueous solutions, so we are always fighting with the unwanted hydrogen evolution on negative electrode and potential damage of our carbon-based electrodes on the positive electrode by elevated potentials during charging. So with that stack EIS, we can truly see what is going on inside. So how to use EIS? We can definitely use it as a tool of quality control for manufactured stack. For that, I would definitely appreciate if all the stack manufacturers could somehow preserve electrical contact on each cell, and then all customers can just double check the quality of their stacks. Another aspect is when somebody is playing with redox flow battery stack design. So with stack EIS, you have actually a tool that will allow you to see inside. So when you will be playing with some non-symmetries at side of electrochemistry, at side of chemistry, but also at side of design of the electrode zones, you have now the tool that will allow you to look inside. We are implementing the stack EIS into our kilowatt-rig units, and we are now getting to the point that we will move from our lab-sized laboratory to our semi-industrial unit. So let me at this point terminate my presentation, and I will move to the unit that I plan to introduce in more detail. Okay, so let's go from our lab to our semi-industrial laboratory. Okay, so wait for the stabilization of that screen. Very good. So everything is working now. What you can see in the middle of screen, that is our kilowatt scale test rig. The orange part of the system, that is actually our redox flow battery stack. The active area of individual electrodes is 608 square centimeters. We have 20 cells electrically in series, and the hydraulic distribution is parallel. The electrolytes are brought from the yellow-gray tanks that are below the orange stack. So we are using welded polypropylene tanks that are filled with 70 liters of electrolyte on each side. So it means 70 liters of positive, 70 liters of negative. It is roughly giving something like 2.5 kilowatt hour. The stack power rating, the nominal power is something like 2 kilowatts, let's say. You can see that on top there is a red and black wire that is going into the stack. So that is electrode connection. I will comment that later. But before that, you can also see that hydraulic loop that is going into the stack. So I will go a little bit closer, where I will comment in detail. So here we can see the stack from another perspective. You can see the tubing. And at the bottom of the unit, there are centrifugal pumps. They are below the tank. They are black or dark blue. And we are pumping electrolyte from the yellow-gray vessels through the flow meters and through this tubing inside the redox flow battery stack. We are using our own control unit with our control software for operation, for control of the system, and for data acquisition from all the sensors. And next to the unit, there is also power electronics. We are using bidirectional power source, power load. And today, it goes through the EIS unit from Colibri that we have here. So now let me comment a little bit more the electrical connection. The stack on top is connected through the EIS unit to the bidirectional power source power load. The bidirectional power source power load provide the basic unit, especially for charging of the system. And then in the EIS unit, it is actually splitted. One part of that, the bottom part, that is stack load, where so it means that the Polybrick system comprises its own internal load. I can show you a little bit more from the back, where you can see that red and black blue labeled cable that goes from the bidirectional power source. Power load, and then on the other pins after EIS, on that orange copper terminals, they go to the stack. The internal capacity, the load capacity can be something up to tens of kilowatts. So it means that also some cooling is necessary. You can see that the hydraulic manifolds with that brass vertical line with blue and red tubings that are entering into the load, but the miracles are actually happening on top in that stack EIS. That is the place where the modulation of that constant current signal is happening. And this modulated signal we are bringing to the stack terminals on top of the system. So it is that we have now AC that we can control and bring to the system or take from the system. And then we have also sensing units. And you can see that it is pretty abundant system. We are only using 3 channels. Each channel here is tailored for sensing of 8 cells. And through these probes, I will continue with these probes. So we are ending here. We are bringing the red and black sense wires on the electrical connections inside the redox flow battery stack. On top, there are also another probes that are the blue boxes from which we are sensing the stack voltages. Okay, so that is in general the system. It will be a little bit loud. I will leave my colleague to turn the unit on, and we will move into another room where we will be controlling the unit on the remote basis. So let me stick back to my computer, and I will share my screen shortly again. So okay, and here we are now inside the computer, inside our control unit that is driving the system. And I will hand over the board to Jiří Charvat, who's operating the unit today.
So right now we will start with some real-time demonstration of the unit itself. But at first we need to be sure that the unit is prepared for it. So at the beginning, I will just start the pumps. So I started the pumps. You may see that there is marked in green, and also you may observe that the flow rates are increasing as well as the pressures. So we can see that the electrolyte right now is actually flowing through the battery stack. So now I will go to the.
Can we perhaps comment when we look on the tanks, we can see that there is that defined volume of electrolytes. It is a little bit more than I have expected. And we can see also that the temperature of electrolytes is 27, 28 for negative, 26 for positive. We are also sensing the open circuit voltage cell. You can see that here. And then we are also sensing the pressure, electrolyte pressure on inlet. So we have right now something like 0.9 bars on stack inlet. On the stack outlet, it is going just back to the vessel, so practically no pressure. And also we see the temperature on stack inlet and temperature on stack outlet. And as you can see, we have 30 degrees in our semi-industrial lab. We are enjoying very hot days here in Czechia.
So now we will go to second part of this of the program, where we might change actually the bidirectional power source units, as was described by my colleague Jiří. We want to do measurement right now, and as you know probably from lab measurements, the absolute majority of the EIS measurement is done during OCV. In lab, it's quite easy because with the potentiostat you can do it very easily, but in this larger scale, it's not that straightforward. So you actually need external power source to give some positive, for example, charging current, and then you use the load inside of the Colibri Mega EIS, and afterwards you are able to work around OCV. So right now I will start charging the battery stack with 50 amps, and here in this graph on the right you can see that we are charging with 50 amps. You can see the response from the voltage of the battery stack, and you can see that right now we are charging the battery stack is approximately 1.5 kilowatt. Now I will switch to the second window for the Colibri instrument, and here you can see right now that we are charging the battery stack with this 50 amps. But as I mentioned before, we would like to do the measurement around OCV. So we will set the same current, the same discharging current by the external load. So now I will set the same current with external load. And now you can see that actually the battery stack is around OCV.
So it means practically zero amperes inside the system.
Okay, but what it also means that we do it with this charging and discharging current, because for EIS measurement we need to do some modulation, and right now from this 50 amps of discharging we can do modulation up and down. So the amplitude of this current load will be set to 20 amps. Otherwise, I will start some experiment. Some experiment will be relatively short, because if you want to measure all this very nice data with mass transport limitation, you would need to make a relatively long measurement, and we haven't got enough time for that. So for that measurement, the amplitude will be 20 amps. The starting frequency would be 30 kilohertz, and we will go just to 1 hertz. Now I will start the measurement. So I will press the frequency scan.
Now the magic is happening.
Now the magic is happening, and we can directly look we can directly look that there are these sinus wavelength. The yellow one is the current, and the blue and green are stack voltages. So you can nicely see just during the measurement all the sinus wavelength I do think that this is absolutely great, because in the absolute majority of even potentiostat, you cannot see actually the magic. You cannot see the wavelength. You just get some results, you get some Nyquist plot and so on, but you don't know what is actually happening. Here you get all the raw data, and if you want to do some of your own post-processing, you want to do some of your own Fourier transformation, everything is possible for you, and you can do it. So I do really love how this system is really open for you, and you got all the data. So the measurement just finished. So we will go back, and here are some results. So we got this Nyquist plot of whole battery stack or individual cells. Now I will just show that we cannot also do the measurement not just around OCV, but for example during the discharging of the battery stack. So now I will switch to the second window. Now I will turn the charging current. So the current is 0, power is 0, and when I will go back again, you can see that right now we are discharging the battery stack with 50 amps. All other settings will remain the same. So again, the amplitude would be 20 amps, but we will measure this under the current load of 50 amps.
Before we will turn that on, in this right window, you can actually see the voltages of individual cells. So what I truly like on this software, that you have very great overview about your stack. You always see what is going on, and this transparency, it is something what we truly need to have as a researchers, and Colibric is very open in the way how they are presenting the gain data from their software.
So now we will start the measurement. So I will press frequency scan. And again, we can directly look for the wavelengths. Yeah. You can see that at the beginning, the green one is a little bit different from the blue one, and it was because that the green one is measured through the power cables, so it's affected by the current itself. But the green one was measured by is measured by sense cable, so without all these effects. Again, the measurement has just finished, so I will go back. There. Okay, and again, here are results. If you would look for results from that measurement and from the previous measurement, you may see that actually the results are pretty the same, and it is due to the fact that this is a unidirectional battery, and here the kinetic is, for example, not as sluggish as in case of fuel cell, where oxygen reaction is it's really sluggish. And in the case of fuel cell, you would observe that charge transfer resistance is actually decreasing for if you will measure it under the load. But for unidirectional batteries, the results are more or less the same. Now I will present you some older results which I measured before this session. So I will load some older data. Okay. Yeah, the data are relatively big, so we need to wait a few seconds. Okay. And yeah, great. And here you can see the whole spectra, including the mass transfer. So here from the spectra, you can see that this intercept. Okay. From this intercept, you can estimate the ohmic resistance, the diameter of that semicircle give you the charge transfer resistance, and diameter of the semicircle give you information about the mass transfer resistance. Yep. Okay, and here you can see results from individual cells. And you can see that this was here, it was measured with relatively high flow rate, so there is very, very low mass transfer limitation. Now I will load some other data which were measured with much lower flow rate. And again, I will mark all the individual cells. And now if you will observe this, so this intercept, again, the ohmic resistance is the same as in during the previous measurement. The charge transfer is again the same, but the last semicircle is much, much, much bigger and give you information that this measurement was done with lower flow rate.
What is also very nice here, that you can see that there is certain distribution in ohmic resistances as we are working with carbon felts. There is certain level of inhomogeneity. So from the distribution of those resistances, you can see that also the material on the input shows certain quality. So you can also double check how good is your stack design or how good is the supplier of your active materials.
And the last thing which I would like to show you, that even though you got the great battery, you got the great mega EIS, you need to be very, very careful about how you connect it together, because these measurements which I will present to you were measured with the same battery stack, with the same unit. The only difference is the connection. And here the problem was that here in your power cables, a relatively high current is flowing through them, and this might cause some inductance around them. And if these cables are too close to your sensing cables, it would actually affect your measurement and you are not able to see absolutely anything. So it should be like last warning. Even though you have this all great system, you should be very, very aware how you connect everything together and what's your final connection, and you still need to think about it.
Yeah, it is exactly like that. You can work with excellent devices, but the way how you will connect them can always influence the system. Of course, the Nyquist plot, that is the most important thing for us typically, but I also know that in other fields, somebody might like the body representation or that standard representation. So all that features of that software are included. It was just very short introduction of those things that we feel that they are relevant for flow batteries. I also hope that it was inspiring and that you have enjoyed the look perhaps on new technology, because we know that flow batteries are not in the main scope for energy storage. So it is slightly new topic, although that they were developed already in 60s. Actually, vanadium flow batteries are celebrating 40 years anniversary. They were invented in Australia, so this year we are celebrating, and of course we are developing. Thank you for your attention, and I will hand over to Radek from Kolibrik.
Hello, everyone. Hello, everyone. My name is. Just a moment, please. Okay. Hello, everyone. My name is Radek Novák. I am a sales manager at Kolibrik. At first, I would like to say thank you to Gamri Instrument for hosting this event. And also thanks to all of you who joined and who is interested in this topic. Then I would like to say thank you to Pinflow Energy Storage. They are one of our very faithful and long-term customer. They keep buying our cell voltage monitoring, our high current potential stats, and they also bought now the first Mega EIS system, similar system that they presented today. So I would like to really thank them for actually sharing their practical experience with our system, sharing the benefits and seeing it from practical point of view. The last but not least, I would like to say thank you to Kolibrik team and especially the development, because they allow me to sell such a system that is very useful in practical applications. We have received many inquiries for this system in the past. We, as a company, our mission is to help the transition for the renewable energies. Yeah, so we are primarily focused on hydrogen, but also on the electricity and the battery industry. Our system was for some time very useful for the analysis of electrolyzers and the fuel cells. Nevertheless, we were getting the feedback from the battery industry that they need to measure the EIS on the level of the cells at 0 DC current, not when it's charging or discharging. So actually, I can thank to our development team that worked hard on it, and now we have a solution that was presented by Pinflow that we can provide solution to you. If you need to measure a multi-channel solution, a large number of the cells with voltage up to 1000 volts, with current up to 1000 or 2000 amps, it can be also boosted. But what's the most important, not just when you're charging or discharging the batteries, but at 0 DC current. As it was already mentioned, it's a very modular system. So I would be very interested to hear from you what is your expectation from such a system, what would be your requirements. So it would be great if you see this as interesting and it could support you with your development, that you can come to us and we can help you to design the system that will fit your needs. And you can come to us directly to Kolibrik. We are based in Europe, but you can also contact some of our partners, Gamri Instruments in USA, but we have partners all over the world. So please contact us and we can direct you to local partner or the closest partner if you wish. So I think this is all from my side. And now I'm handing this back to Gamri.
Okay, thank you again for the talk and everything. Let me. Is that you, Roddick? I need to mute you. I wanted to open the floor if anybody had any questions about the experiments they saw. Everybody's been fairly quiet during the meeting. There was one thing I was kind of interested in. So you induced the error you saw on one of the channels, and the EIS system pointed that out. In practice, with your real systems, do you see lots of errors getting pointed out? Maybe not quite so large and distinct, but do you see the variations just in the regular cells that immediately identify that one or some of the cells are not operating properly? Oh, let me unmute you, Yuri, so you can answer the question.
Thank you very much. Can we just go through the question again? I was fighting with the connection. Can you please repeat?
I was. So you had the example of the induced error you found on one of the channels. I was wondering if maybe just a description of these errors you see in real practice and how.
Well, typically, it goes to the manufacturing praxis of the redox flow battery stacks. When I will come back to that, my last slide in the presentation, I will mirror the chart again. How the typical manufacture of flow battery stacks is happening? That is that you are typically using CNC milling. You are manufacturing the stacks by this technique, the individual plastic flow frames. Then it is the first method for prototyping. When you will grow, you are typically switching to compression molding of flow frames that can significantly decrease the cost because we are willing to decrease the price of the system, so we need to increase the scale of the manufacture. But the issue in CNC milling might be that actually there might be some residuals of plastics and that the paths are not so smooth. So while we were testing flow rate limitation in one cell, imagine the situation that you have solid particle that is not reacting with your electrolyte and that gets stuck inside the stack in one of the cells. The particle is delivered into the cell through the electrolyte manifold. It is flotating in the electrolyte, and then it will get somewhere stuck. It might happen on the stack inlet, it might happen inside the flow channel. And by this approach, by this simulation that we have physically conducted, we just wanted to know what is actually the real contribution to influence of the potentials, electrode potentials in individual cells. So that was our motivation. From the perspective of the manufacturers, we know that this might be an issue that doesn't allow you to detect the problem after 1 week of operation. You will typically see this problem after several months of operation. So you must be very careful about it. And in order to preserve good quality of our products, we are even conducting research like this to deliver the best value to our customers.
I had a couple other questions pop up as well. Schrader was asking if you had any further explanation about how the bidirectional power source or load work together with the Mega EIS system.
Yeah. Okay, I will try to answer a question. Normally, if you are working in lab, you get potentiostat, and you can do the modulation of your voltage even around the zero. But here you got just load, and you cannot do modulation right around the zero. So you actually need this bidirectional power source, which give you some, let's say, charging current. Then you use the same discharging current with this power load, and you got this power load discharging current at some value, and actually you can do the modulation with this discharging current. So here, this discharging current was 50 amps, and we did this 20 amp modulations up and down. So we were, so we did this modulation, and this is the reason why you actually need this external power source. Yeah.
It means we are not working with potentiostat. We were not working with potentiostat today. It is stack electrochemical impedance spectroscopy measurement. The principle is a little bit different, and that is the reason why we need to have also the power source for the system. Perhaps I will continue. There is one good question from He Yushu. Does it possible to do EIS of redox flow battery under charge discharge conditions? Exactly. That is the thing which you can do with this system, and that is how it is designed. We are very focused on that OCV mode. That is where we can gain the interconnection between the lab scale research data with real systems. That it was the question of Ali Gol Mohammadi, and that is that interconnection with literature that we need to know. We need to have transferability from lab scale to pilot scale. We need to understand what is going on, how aligned are we with the laboratory data. So that is the motivation why OCV is so interesting. And also from another perspective, it is tricky from the perspective of manufacturers of such a system, because you are dealing with pretty high currents over, or let's say around 0 amps. So you need somehow deal with this. But I agree that the EIS under load might be very important, especially for those of you that are working with non-homogeneous systems. In our vanadium redox flow battery, we have a very homogeneous environment. Both electrodes have liquids inside, and the electrochemical reactions happens only at the surface of the three-dimensional electrode. But when the things are a bit more complicated, like non-symmetrical setups, for example, different phases in one of the half cell, it can be, for example, some metal air system, then the problems appear. And it was like we were talking about it parallel with fuel cells. In fuel cells, you are truly very interested into the load state. You need to know what are the load characteristics when the stack is loaded. You need to understand the dynamics of the transport phenomena. But typically in vanadium redox flow batteries, it is not so significant issue. And we like to have the possibility not only work at load, at charging and discharging, but the possibility to measure the data under OCV and compare that from data from lab size systems is transferability. That is the interesting thing that we see here.
Okay, if I may answer the other questions from Max about the frequency ranges. Actually, the answer is not that easy, mainly with the high frequency, because each individual cell and stack, you need to find actually which frequency do you need. For example, in our smaller laboratory cells, we need different ranges than with the stack, but basically these measurements were performed from this 30 kilohertz, and this whole spectrum were till 1 millihertz, but it is probably not necessary to go that low, and the time is affected. How smooth do you need the spectra? So how many points per decade, and how many times do you actually measure the wave, the sinus wavelength? But let's say that if you want like the whole spectra, including the mass transfer, let's say the measurement will take like 1 hour or something such.
And there was another question Mason Lyons just submitted about stability in the measurements, particularly with the discharge currents.
So how is the system stable or not drifting to make quality EIS measurement during charge, discharge, or OCV? For example, with when 50 amps discharge and 20 amps EIS modulation, how does that not affect state of redox flow battery?
Of course, it's best to work around OCV, because in that case you are not charging and discharging your battery. So if you want to do measurement, the long measurement, even with this mass transfer, which can take, let's say, this 1 hour, I would always do the measurement around OCV. But for this measurement, when you don't need the mass transfer, but you are okay just with ohmic resistance and charge transfer resistance, which take, let's say, till 1 minute, then it's absolutely okay to do it during the discharging or charging.
So it means it is about the experimental setup. It is how you will set the parameters and how you will design your experimental unit. It is also related to the system design. With our kilowatt rig, we have the capacity to power ratio something like 1:1 or a little bit more capacity. But we can play also with this ratio. We can use more electrolyte, larger vessels, then we are less changing the composition of electrolyte during measurement and so on. Yeah, so it is pretty complex questions. And as you can see, we are solving similar things that we are used to solve at laboratory scale. And with tools like that, it is also possible to play very analogously to lab scale, even at the semi-industrial scale.
I think that, oh.
Yeah, mass transfer is
comment
there. Agree with Schroeder.
Yeah.
Schroeder.
Or otherwise you would need really large volume of the electrolyte.
Well, there is very good question about the repeatability of measurements. The difference in ohmic resistances be due to measurement error. Well, it is again about the system setting. That is what we were solving very patiently with Colibri, how to set the parameters of the unit that is necessary for redox flow batteries. Always we need to consider how large are the tested stacks. So that is where we were bringing the knowledge of the community from flow batteries. We were considering different electrode sizes. Then Colibri evaluated, they were asking us about maximal current. So we were following what we know from the literature, from our systems. So somehow as nominal, we have considered 150 milliamperes per square centimeter as the nominal value, with some maximums up to, let's say, 300 milliamperes per square centimeter. And then the system design of that electrical side was led by Colibri specialist, and we have truly delivered the system with excellent accuracy for our application. So it means that we are having very smooth data with very good reproducibility. Then the other thing regarding the reproducibility is the quality of carbon fiber electrodes. I expect that Giacomo is following the affiliation, well familiar with flow batteries. So we all know what are the differences of properties of individual felts. We are fighting with, let's say, plus minus 5 to 10% of weight differences and so on. So it means that there is always some ohmic resistance distribution. Thank you.
And a couple more comments there. Did we have any other questions from any of our participants, attendees today? No.
Okay, so perhaps before we will quit, I have seen that there is also few people from the flow battery community. So for those who are attending International Flow Battery Forum starting on Monday the next week in Glasgow, I'm inviting you to visit our booth. We will be exhibiting there, and I'm also inviting you to visit the lecture of Jiří Charvat, who will present a little bit more data also including utilization of this mega EIS. So we will be more scientific, and it will be more for the flow battery community, and we will be very transparent in benchmarking of our redox flow battery stack. So it means we will let you look under the carpet here in PinFlow, and see you in Glasgow for those who are attending. And thank you very much to Colibri for their excellent support in development of such products that are fulfilling the needs of our community. And thank you also to Gamre for organizing this event.
Yes, you're very welcome.